All right. Okay, let's get started. Hello, everyone. My name is Yu Feng, and I'm a CEO of Veridice, a startup that is focusing on building tooling for blockchain security. And I'm also a computer science professor at University of California, Santa Barbara, in which I do research in formal verifications and security. So, speaking of blockchain, so I just want to start by stating the very obvious thing in a sense that so every software has bugs, but bugs in blockchain software are extremely costly. Okay, for instance, any bugs in the blockchain layer can be lead to catastrophe effect when it gets deployed. So here by blockchain software, I'm referring to let's say blockchain consensus protocol at the lowest level, all the way up to zero-knowledge circuit, and as well as smart contract, as well as Web3 applications. In the sense that if you have any bugs in any of those layers, so the attacker might be able to leverage this kind of problem and then steal tens of thousands of dollars. So here, I just want to give you an example. I think probably this is pretty well known in the smart contract developer community, in the sense that I think recently a protocol called Beanstalk, it was hacked by over 182 million worth of dollars. And then one of the root cause of this bug is actually because of the flash loan attack. So in this case, if you are a Cairo programmer, you might saying, well, who care about this, right? This just happens on Solidity, on Ethereum. So we are good. We are writing Cairo on StarkNet, but are we really safe? I hope that no one can say that, right? Because as StarkNet ecosystem become more and more popular, there will be more and more fund and money that stake on the protocol. It's just a matter of time the attacker get to there. So how are we going to do that? Okay. So I'm going to unroll the show by following this outline in a sense that so I'm going to give everybody very, very brief overview about what's formal method. And then after that, I will go over the tooling that we have been working on using a concrete example from OpenZeppelin. And then I'm going to wrap up a talk with some ongoing future plan. Okay. Okay, so before we get started, so what's formal method? Okay, because I believe that this terminology has been overloaded by the community, including developer and auditor a lot. So the textbook definition of formal method, essentially, it's a set of mathematical rigorous technique for reason about your software. And then the goal is essentially either to find bugs if it exists, or it gives you a proof in the sense that to certify that your software is actually free from a class or bugs. Okay? So in this case, you might wonder, so why do we care about formal method? Right? For instance, if you are rich, let's say I want to buy the latest version of Mercedes E-Series, which contain tens of thousands of sensors. And then every sensor has a bunch of options. For instance, before the engineer ship the car to you, it's actually perform rigorous formal verifications. Because you don't want to, the engineer just by staring your source code and then give you the car, right? So in this case, when I say formal method, okay, so here, so I'm not just referring to a single technique. For instance, you might have heard of some of them in the sense that I'm actually referring to a class of technique. So from the left-hand side, that contain dynamic testing, such as fuzzer. In this case, probably you're familiar with Foundry. And then all the way to the right, you can do static analysis based on abstract interpretations. For instance, here you can use Slider. And then all the way to the right extreme, which is essentially formal verifications. For instance, right now you can use the K framework from runtime verification. And then basically, there's, as you can see from this spectrum, there's not a single technique can solve everything. Okay? In the sense that if you go from left to right, so basically your guarantee essentially gets stronger. However, just like life, in the sense that there was no free lunch. So in order to get stronger guarantee, it requires more manual effort. Okay? For instance, if you want to use Foundry for doing the fuzzing, you basically don't need to do much. And then essentially, you just need to set up the framework, and then it's going to execute and exercise the program for you. Whereas if you want to do formal verifications with, let's say, the K framework, So as a developer, you have to provide this kind of a manual formal specifications for the tool to verify. And then that will take a huge amount of effort. Okay? And then if you look into those techniques a little bit closely, so they can also divide it into two categories. Okay? On the left-hand side, we have those kind of dynamic technique. So essentially, the idea of dynamic techniques is essentially it tries to exercise your program, okay? Dynamic exercise your program with some interesting input. So by interesting, in the sense that you generate some concrete input, and then you exercise your program, and then you observe the behavior. And then the idea is that you hope to observe something bad. So before you actually deploy that to, let's say, StarkNet. Okay? And then on the right-hand side, we also have static technique. For instance, including abstract interpretations as well as formal verifications. So basically, the idea of static analysis or formal verification is essentially, you can think of it statically stare at your program. Okay? It didn't run your program at all. It just statically stare at your program and then try to reason about all possible paths. Okay? And then try to find whether there exists any execution that can potentially lead to bugs. So as you might be wondering, so if that's the case, why do I choose the one on the right-hand side? Because like the right-hand side seems more thorough, right? Because it is modeling, it's trying to model the executions of all possible execution, not just a single pass. So that's essentially the advantage of static technique in the sense that it can allow you to reason about all execution as opposed to a single execution. And also, it can allow you to find bugs as well as certify your program in a sense that if your program is safe, I can actually give you a concrete proof to show that your program is going to be safe. However, just like I mentioned, there's no free lunch in a sense that, so formal verification in general is undecidable. Undecidable in a sense that if you want to get this kind of guarantee, so one of the things you have to suffer is essentially false positive. Right? For instance, if any of the smart contract developer, if you have any experience on running static analysis on your smart contracts, such as Slider on Solidity, so you realize that it actually generates tons of false positive. And the false positive is so high, and sometimes you just give up like using the tool. And on the other hand, so if you look at the dynamic technique on the left-hand side, so the nice thing is essentially there will zero false positive in the sense that every time the dynamic technique is going to give you, it's going to be a concrete exploit, such as Foundry, right? If you run Foundry on your smart contract, you realize there's a bug, it's going to be a concrete bug. But the problem is that you don't get much guarantee in the sense that it's a bug finder that tries to help you to expose as many bugs as possible. But let's say I use dynamic technique to exercise my program for a year. Okay? And then it doesn't mean that your DeFi is going to be safe. It just means that within this year's amount of time, I try to exercise as many chases and space as possible. I didn't find anything suspicious. But it didn't say anything. It cannot give you anything about the future. So that's what I mean by it cannot give you any guarantee. Okay, so which means that at the end of the day, so when we talk about formal verification for blockchain or smart contracts, so everything is essentially about trade-off. There's not a single technique that can rule everything. So in a sense that if you want to go more on the right-hand side, you get stronger guarantee, but you also need to put more manual effort. However, okay, that's a big however, in the sense that that only holds for Solidity. Okay, for instance, if you are a Solidity smart contract developer, so you will have a lot of choices. Okay, you have a lot of choices from left-hand side to the right-hand side. However, if you are a Cairo contract developer for StarkNet, so basically you're almost on your own, right? So in a sense that basically there's not a single tooling, so to my best of knowledge, that can do any of those for you. So that's essentially the goal for today. So that's essentially the tool I'm going to introduce, which is called Magile. So essentially the overview of the system in the sense that you can think of on the left-hand side, it take input as a Cairo program. Okay? And then, so the tool is going to leverage the Cairo default compiler to essentially generate its corresponding bytecode. And then the bytecode essentially the the granularity in which our veridize tooling is going to operate on. Okay? For instance, in the current talks, in this talk, I'm going to introduce the formal verifier that we recently built. And because of it's a formal verifier, which means that one of the necessary input is the spec, right? So in order for me to verify the correctness of your program, you need to tell me what's correct. So that's essentially the goal of the formal spec. And in the near future, we also plan to essentially integrate the Cairo front end with our existing pipeline for doing common vulnerability detector using static analysis as well as a goal-directed fuzzer. Okay? And in today's talk, I'm just going to focusing on the formal verifier, which is essentially the one that actually gives you the strongest guarantee. Okay, so let's before I actually go into the detail of the tool, let's go over with a concrete example. Okay, I'm pretty sure that, by the way, how many of you are actually writing Cairo smart contract? Can you raise your hand? Okay, a decent amount. And then, so this is actually, I hope that everyone should be able to familiar with this piece of code. It's actually from OpenZeppelin, the ERC20 token, and then this is essentially a main function that allows you to create a certain amount of tokens, and because you create a certain amount of tokens, you have to update your storage variable accordingly. Okay, so now, for those of you who are actually writing Cairo smart contract, can you tell me where is the vulnerabilities in this program in 10 seconds? This is a very, very like a kindergarten like a version of vulnerabilities. Like just 10 seconds, can someone tell me? Yes? Oh, no, it's actually not that sophisticated. So by the way, if you cannot identify the vulnerability of this piece of code, so please tell me the name of your startup so that I can avoid depositing money on your protocol. So essentially, this is a very baby version of vulnerability in the sense that, so let's say I try to create a certain amount of tokens, and then because I create a certain amount of tokens, so which means that my balance get updated, right? So that's why I need to increase my balance by this new amount. And then this is essentially going to return to this new storage variable, new balance. However, what happens if this amount is going to be a big number, right? So if this amount is a big number, when you do the modifications, when you do the addition, it can overflow. It can overflow. So that's essentially the original bugs from OpenZeppelin. In the sense that even for OpenZeppelin team, they can make this mistake. So I'm pretty sure that this is not quite uncommon in reality. So now the question is that, how do you fix that? Can someone tell me how to fix this problem? Yes.
Use safe methods for addition.
Mm-hmm. Yeah, so the answer is that you use safe method for addition. Essentially, you want to add some additional assertion to avoid overflow. Essentially, that's exact the fix. Okay, for instance, if you look at, for instance, in this case, if you look at the fix from OpenZeppelin, essentially what it does, essentially, at the end of the like arithmetic operation, it tries to assert that no overflow should allow happen, right? So as you can see, once you understand the bugs, fixing the bug is actually super, super easy. But the question is that, how do you identify this bug from the very beginning, right? So you don't want the attacker to tell you that there is a bug, right? It's already too late. So, so which means, how do you find this bug from the very beginning? And once you fix the bug, how do you guarantee that your bug is actually fixed in the sense that there was not any other edge case that can be leveraged by the attacker? So that's essentially the technique we are going to use, which is called symbolic executions. Okay, so in this case, I'm going to take one slice of detour to talk about the idea behind that, just from a very, very high level perspective. For instance, here, let's forget about smart contract. Let's forget about like a blockchain. Let's just use let's say another kindergarten example. Okay, this is a function which is very trivial. Okay, so it just returns whatever that is largest given to integer. Okay, So in this case, if I execute this program with some concrete input, for instance, I try to compute the max between 1 and 2, not surprised, it's going to return 2. And then if I try to compute the max between 4 and 3, I'm going to return 4, right? This is what's happening on the concrete world. So now the question is that, so what happens if I don't just want to reason about one concrete execution, but the space of all possible execution? Okay, in this case, as you can see, this essentially represents that this is essentially the universal quantifier. In a sense, I want to say that for arbitrary x, as well as for arbitrary y of those like arguments, I want to know what's the behavior of these functions. Okay, so and obviously the result that you're going to like ask this kind of is essentially it's not going to be a concrete value anymore. So essentially, this is essentially what you obtain. So this essentially, as you can see, this is essentially a mathematical formula. This is essentially a mathematical formula that represents the behavior of all possible space of your program. In the sense that this essentially asserts that for arbitrary x and arbitrary y, so if you pass me x and y to these functions, I'm going to return the value of y if x is less than y. Otherwise, I'm going to return x, right? So this is essentially the mathematical definitions of the behavior of your original program. So now, in this case, since you already represent the space of all possible programs using a mathematical representations, you might wondering, who care about this, right? Why do we bother like generate this expression? The reason that you want this expression is that at the end of the day, so you want to reason about the property of your behavior. For instance, in this case, you might want to reason about some safety property of your behavior, right? In this case, so which means that this expression is essentially denote that for arbitrary x and y, if I symbolically execute this program, which essentially represent as this expression, at the end of the executions, does it imply, this is essentially the implication, does it imply any property that I don't want to see or any property that I would like to see? Okay, for instance, this property can be nasty reinsurance attack, it can be flash-on attack, or it can be some simple properties such as like a arithmetic overflow, like the example that I showed you. And then once you generate this kind of a mathematical representations, you can actually send it to an oracle, which will be answering the questions of this query. And then the oracle is typically done by an off-the-shelf, like as a constraint solver, such as these three. Okay? So this is essentially basically symbolic execution one-on-one. And then you might wondering, how does that relevant to our original case, right? For instance, in this case, I have my original program on this slide, and then I want to see whether like there's any bugs or whether I can verify that my program is actually safe. So all you need to do to use the tool, essentially, you just need to add one single statement, okay, which is called verify, and then you pass the verified functions with the constraint that you want to verify. For instance, in this case, I want to verify the new balance should always greater than the original balance. Okay, let's say there's no negative like a number. So in this case, so notice that this is very different from, let's say, the runtime assertion that you add. In the sense that when you add runtime assertion, using assert, this assert will only fail if you actually pass a concrete runtime value that will fail your assertion. So this verify is essentially trying to reason about the space of all possible integer that can allow for this new balance. Okay, this is essentially like verify in the sense that for arbitrary new balance as well as arbitrary value of balance, is there any way that you can fail this assertion? Okay, and then so in the end, so what the tool is doing is essentially it's doing the same thing as the max example that I showed you earlier, in the sense that it converts the current program into a mathematical formula, okay, in which the formula can be essentially represent the space of opposite behavior of the current functions. And then what the tool does is essentially it's trying to search for a counterexample. A counterexample in the sense that whether you can actually, if there exists a bugs, you can actually find a counterexample that fail my current assertions. Okay? So because of the device limitation, I cannot do the demo, but you can actually try it out with our GitHub page. So here I'm just trying to give you a screenshot of the output of the tool, in the sense that in this case, let's say if you compile the original buggy version of the Cairo contract into the bytecode, and then you fit to our tool, so this is essentially the output that you get, in the sense that the tool is going to tell you that, hey, so I can actually find a counterexample that essentially going to fail the verifier statement that you try to enforce. And then in here, you might wondering, so why this amount is not one like U in 256, but it's going to be a tuple. So this is because of the data structure of the Cairo. In Cairo, so all those numbers are essentially finite field. And then in particular, those finite field elements, they are represented as a struct, which is using low and height. And so that's why the way we handle that is essentially we use a symbolic variable to represent the low and high part of the number, and then ask the tool essentially to show us a counterexample that is going to fail the assertion. And then on the other hand, if you actually provide the fixed versions of the contract, which is the one I showed you earlier, to the tool, so the tool was actually can give you the certification in the sense that I try to search for the space of all possible behavior, I actually cannot find any counterexample. So which means that in that case, your contract is actually safe. Well, here by saying safe, it's only guaranteed that it's going to save with respect to the overflow property that you're trying to verify. Of course, in order to verify other property, you have to specify your query, okay? So then you might wondering, so this seems to work, but that sounds like only work for toy example. Okay, so can you do something more interesting? Well, this is actually what we have been working on in the past few weeks. So this is essentially the specification we just formally verify for the MakerDAO protocol. For instance, right now we are actually working with the MakerDAO Cairo team to formally verify their implementations, and then the way we do the verification essentially. Right now, we directly took the specification from the original specification of MakerDAO written by the Satora approver. And then this is essentially the specification from the original Satora approver. And so in the near future, we plan to gradually switch the specification from the Satora specification language into our own specification language, because which will be more concise and then require significant amount of effort for less effort for writing spec. Okay? So this is essentially how the tool looks like. And then from the short-term plan, so what we want to do is essentially we want to completely verify a non-trivial protocol. So by this month, and then so after that we are also going to provide more tutorial and the documentations, so that to engage with the community. And then that's essentially the short-term perspective regarding the tool I just showed you, which is essentially a verifier. And from the long-term perspective, so what we plan to do is essentially if you get a chance to attend our ECC talk yesterday, as well as checking out the profile of our co-founders, you realize that we have been actually building a serious tooling for blockchain during the past 5 years, including static analysis for checking common vulnerabilities, as well as a goal-directed fuzzer, which is a lot more effective than the open source fuzzer you can find right now. And what's mostly cool is about this attack synthesis framework called Euros. Essentially, if you have a bug, let's say fresh loan, so our tool can actually concretely generate an attacker contract for you. So our next step is essentially to build an adapter to essentially adapt the Cairo contract into our intermediate representation, such that we can leverage all the essential pipeline from Veradice. And so, right. Yeah, that's pretty much. And then I want to thank you, our amazing team. And without them, I think nothing will happen. And I also want to thank the StarkNet ecosystem, as well as our amazing VC for sponsoring this work. And then if you are interested, feel free to scan this QR code. And also, like, we are also hiring. So if you are interested in position in Veradice, feel free to reach out to us.